So, okay, we're on. Today we're gonna go through the introduction course chapter of the book. Hopefully you can see my screen now. Okay, so this is an introduction to fluid mechanics. Most of you read the book already, but today we're gonna go into very basic stuff of fluids. So we're clear on what we're talking about. So we'll go through what is a fluid and some basic properties of fluid: density, viscosity, pressure, bulk modulus, and surface tension. Hopefully we can cover all of this relatively easily. And we're going to solve a couple of problems that I think are key. I mean, some of these are really simple concepts, or should be relatively simple, but there are a couple of concepts that are really key to fluid mechanics. So it's important that we cover them in a bit more of detail. So, what is a fluid? I remember when I took this very same lesson. It was in another university though, but I was younger, and my concept of fluid was something that took the shape of the container it is in, and that is something of a school level definition. Is probably something that I would tell my kids. But by that definition, cats, they look like fluids, right? They can take the shape of whatever they're in. So it's not a very handy definition, and it's wrong on the basis. So what is a fluid, if not that? Well, there are formal definitions. This is one, and I'm going to read it out loud. It's a substance that will deform in quantities that are not necessarily small. That means that it can deform a lot in an irreversible way when submitted to a small force. But that still is it's not very clarifying. So here's a classic image. So I want to delve a bit into this image, and for that I'm going to try to use some sort of blackboard. Just bear with me. Let me see if I can do this. You should be seeing my other screen now, right? Okay, great. So, any of you has taken already statics, like structural statics, or physics of materials? The key thing for when you study materials or statics is that the materials deform. So let me draw a free body diagram. So let's say you have a body and you apply a force onto this body. If that force is large enough, what's going to happen is that the body will deform, and it will shift to the right in this case, and it will deform. And once you stop the body, the force, if you stop applying the force, then the body will deform back. You can think on a table. Have you noticed that all tables, what's the name? They're not very stable. All tables wobble because you have 4 legs and you only need 3 legs. And no, I'm not. I'm being asked if I'm writing the presentation. No, I'm writing into some sort of whiteboard. Can you see the whiteboard, or are you watching the presentation now? Don't you see the whiteboard? Let me. Ah, so the whiteboard is being seen. I draw a sketch here. Is it visible? All right. So what I was saying, if you can you see the whiteboard? Yes, I have a couple of yes. No? Yes, yes. All right. When you apply a force into a body, the body, sorry, let me just, no, I cannot change that. Well, we'll see later on how it worked. Just bear with me. Bear with me during this example. Again, when you apply a force onto a body, the body will deform. And in the same way, when you have a table that wobbles, because you only need 3 points of support, so the fourth leg, if it's not exactly well designed, then the fourth leg is going to move, unless you put a very heavy thing onto the table. Then the table is going to deform, and all legs are going to be stuck to the bottom, right? But once you move that weight from the table is going to bounce back. So when you stop applying a force onto a solid body, the body will bounce back to its original position, unless you apply a so extreme force that the body starts to behaving like a fluid. Have you heard about fluidization of steel or something like that? If you apply too much force into a steel beam, for instance, it will start to flow, and then it will not return to its original position. Okay, with fluids, it's the same thing, and actually that's why the name comes from. So let's say this is a bit of strange, but let's say you have a layer fluid. If you have a layer fluid over over the ground, and you somehow apply a force on top of this fluid. The typical example is if you put a lid or a cap or a very thin object on top of the fluid, and then you move that object. To move it, you need to apply a force. Then you move that object, and that object is gonna induce onto the fluid a shear stress. And here are 2 things that I want to stress. One is the concept of shear stress, and the other is the concept of no slip. Bear with me. There are two ideas that you need to keep in mind. One is the no slip condition. The no slip condition means that if you have a particle of water here stuck to the bottom, that particle is gonna remain stuck to the bottom. Right near the bottom, the water sticks to the bottom, and the same happens right on top here. A particle of water sticks to this layer that you put on top. So what's going to happen is this layer is going to start moving. It's going to start moving. It's going to displace, and then you're going to have a velocity right under the cap. Whereas at the bottom, you're going to have 0 velocity. So you're going to have a variation of velocity. Velocity is going to be 0 here, and velocity is going to be some value on top. And this might seem like a bit theoretical, but it's actually true. So let me try and show you I think it's very neat experiment. Give me a moment. Yeah, this one. Okay, now, I'm sorry. Okay, I'm sorry. I'm just playing around and it got overloaded. Okay, so maybe you can see now. This is a very simple experiment. It's a a water channel where water is flowing, and the guy doing the experiment is injecting ink with a needle. So maybe you can see the ink there, and he's going to put ink right at the bottom of the channel. You can see the ink flowing, and once he puts the needle in the middle of the channel, the ink flows back with the flow. Whereas the ink at the bottom doesn't move. And you need to actually remove it with your hand to move it. Okay, this is a very simple experiment, but it represents this idea of no slipping. Okay,
Can you repeat it, please?
yes, the theoretical idea is that molecules of water stick to their boundaries. They don't slip. They don't slide. Right? And that looks a bit theoretical, but it's actually true. You can actually show in with this kind of experiment. Now, of course, this is a channel that doesn't have much turbulence, so there are no eddies going around, and it's a steady flow. It's probably a plastic channel, so it doesn't have rugosities at the bottom. But it's actually true at the very small scales. And why it's important? Because all of the rest of how we measure viscosity is related to is based upon this assumption of no slipping. Okay. So back to the presentation. Can you see the presentation now? Okay. So is the presentation on, right? Yeah. Okay. So the difference between a solid and a fluid is that the fluid will deform continuously. Okay. And continuously means that you're not going to have a deformation measured in centimeters or in distance, but you're going to have a continuous deformation. Then your deformation is gonna be measured in velocity. Okay, and that's the main difference. And you can call that the water or the fluid will drain, or that it will yield. It will constantly yield or drain. And that's the main difference. So you can think on a skimboard. You probably done it yourself, or you've seen it at the beach. Basically, you have a very thin layer of water, of ocean, and then you throw on top of that a table, a board, and you actually and there is a very thin layer between the board and the sand underneath. And you can actually jump into the board, and the force that you're putting into the board makes the water under it to deform and actually lets you slide. So actually the board is not touching the sand. It's constantly removing water behind it. It's making it drain. Okay. And the second, so the first concept that is key to this idea is the no slip condition. And the second one is that we're talking about here about forces, but actually in the analysis, we're talking about shear stresses. Okay. And there's two concepts for that. A shear is a stress, is a force that is tangential to a surface. So if we go back to the cats being fluids, if you take a cat and you pet it and you slide your hand over the cat, then you're inducing a shear. Okay. is if you want, is the opposite, or not the opposite, but is orthogonal to a pressure. Pressure is really normal to the surface, and a shear is tangential to the surface. And the other point is that it's a shear stress. It's not a force, it's a stress. And a stress is nothing more than a force divided by an area. So it has units of pressure. But it's important that it is considered as a stress, because for this analysis, we're going to do analysis at points, and at points you don't have the total stress, but the total force, but rather the stress is how it distributes over the surface. Okay, I have a question. In how is a stress different from pressure? It's not. Okay, stress is measured in pressure units. Okay, so I don't know if you guys have taken soil mechanics already, or internal, but all of these pressure and shear stresses are internal forces, meaning that there are forces that if you take a volume of fluid, there are forces that act on the faces of this volume, and some forces are going to compress it in this direction, and some forces are going to try to cut it, right? And all of those forces are measured as forces per unit area. So they have the same unit of pressure, but they act on different directions. Pressure acts normally to the surface. We're going to see that later on. But shear stresses act tangential to the surface. So they are similar, but not exactly the same. They're measured in the same units, but they're not the same. Let's say, again, if you have a table and you put a very heavy object, if you sit on the table, you're putting a pressure on the table. It is a stress because it's a pressure is a stress by definition. But a shear stress will be if you're sitting in the table and a lot of people grab you and they start to dragging you on top of the table. You're going to induce a shear. It's a force that is tangential. Yeah, it's not, in Spanish is esfuerzo de corte. It's not roce, it's corte, because it's not normal. It tries to cut the body. So the units are pressure, but the way they act, that's the difference. So let me jump to the definition. Maybe you'll see. A fluid is a substance that cannot stand shear stresses. Okay, so under a shear stress, a fluid will start to deform. All right, and under a pressure stress, not necessarily will deform. We'll see later on. But the key thing is that a fluid doesn't stand shear stresses, which are forces per unit area applied tangential to the surface. This is a key concept, and I think in the book it's well explained, but this is very important for you to understand. Not because of the definition. I mean, all of you can realize when you see a fluid and when you see a solid, but the way we represent this, we'll see later on, is through the viscosity of the fluid, and that's really the key difference, and it's important for you to understand. So before we move on, are there any questions? Did I make myself clear? Okay. Okay, so that's the okay. That's a formal definition of fluids, and of course, fluids they're normally come in two flavors. They can be liquids and gases. Okay, and liquids, the main difference between those, I mean, what's the difference between what's the difference between the ocean and let's say the clouds? They do behave both like fluids. They can be described by the same equations. The main difference is that gases can be compressed. Okay, and then the difference between pressure, volume, and temperature are important. And normally that's covered more on thermodynamics that probably you've seen or you will see at some point. Whereas liquids, they're very hard to compress. They're normally very stiff. We'll see the exact definition later on, but for all practical purposes, you can consider that they can't be compressed. So a typical example of liquid is water, which is mainly the main thing that we're going to be seeing here. And gas, air. That's a typical example. But yeah, okay. So we're mostly interested on fluids on a global scale, okay? We're not very, for engineering purposes, we don't mind much about the chemistry of the water or the molecules of water, but rather water as a continuum. You know from basic chemistry that water is made out of molecules. Yeah, H2O. So you have a big oxygen atom plus 2 hydrogen atoms, and they are bound together via electromagnetic or how it's called, bonds, and these molecules attract to each other, and it has several chemistry properties. We're not very much interested in any of that, because once you zoom out from the molecules, you can't actually see the molecules. There are spaces, blank spaces between each molecules, but when you open the faucet, what you really see is a continuum stream, right? You don't see each molecule moving on. So we're concerned at this scale when you can consider the fluid and the flow as a continuous thing. So let's take as an example porosity to illustrate this concept. Okay, so porosity, you might know if you're taking soil mechanics or groundwater course, you might know that the soil, the ground, is not solid. It's actually made of grains of little rocks or little sand, and these grains are in contact with each other, and they leave pores. They leave a empty space in between them, right? So if you look at one grain, you may see that the pore can be really, really big compared to the grain. Now, if you see the ground as a whole, you probably don't see each individual pore, but you know it is there. I mean, when you pour water on your garden, you know the water infiltrates the ground because the ground has this space for the water to go in. Okay, so porosity, for instance, for the soil is considered as the proportion of voids over the full volume. This is not very, very important in our course, but it's just to make an example. So for porosity to be meaningful for us in this continuum approach, you really need it to be over a large area. So let's use this example. Let's say this is a checkers, how you call it, a checkers table. So let's say the whites are voids and the blacks are soil. If you look at the red square, you're going to think that all of the soil is made out of voids, right? If you take three, I don't know if you can see the hand on top of the presentation, but if you take 3 squares, then you're gonna see that 5 out of 9 squares are voids, right? And if you continue doing that, eventually you will reach to a number that is more or less half of the squares are void. All right, so you can't look at a particular square, because you are not going to see this general property that we want to characterize. And for water is the same thing. We don't want to see the molecules. We want to see water as a continuum. And for liquids and gases, the typical length scale that you need to look is in the order of 10 to the minus 9 millimeters. So, I mean, this is really small scale. Anything larger than that, you can consider as a continuum, even a drop of water. So for any engineering applications, all of the properties that we're going to see here, you can consider them to be punctual, to be representative of a point in space and in time. And also we're gonna be able to assume that all of these properties will vary smoothly across points and across time, and therefore we're gonna be able to derive them and integrate them and use differential calculus to characterize them. So we're not going to be counting each molecules, but we're going to treat the characteristic of the fluid as if represented a point. Okay. So again, there are properties of continuous media. There are intensive properties that they are punctual. They don't depend on the quantity of the material, and you can consider them to be representative of a point. And there are extensive properties that do depend on the quantity. So a typical example, intensive property is going to be density, and extensive property is going to be the weight. Okay, the density of water is an intensive property, but the weight of, let's say, a jar of water does depend on how much water you're putting into it, right? Okay. So basically, when you remove the full material and you make it and you make it adimensional due to the continuum property, you can, the typical name that you put in on front of that is specific. So density is a specific mass, and heat is a specific heat, and so on. But it's basically is the quantity divided by the full quantity of the complete sample. Okay, and porosity, wouldn't porosity be an extensive property since it doesn't depend on the amount of volume? Yes, it is an extensive property. The point that I was trying to make is with the example is that you need to overpass a specific scale. If you go to the scale of the grains of each grain, then you can't define porosity, because either you see a grain, then you have 0 porosity, or either you see a void, and then you have 100% porosity. So there is a scale, and it's small, over which you can consider this quantities to be representative of a point. So porosity is actually intensive in that it doesn't depend on the full scale. I mean, if you have 1 teaspoon of dirt and you have a truckload of dirt, the porosity is going to be more or less the same. So it's intensive. Whereas the weight is going to be, and the density is going to be more or less the same, and the humidity, etc. But if you take the weight of the teaspoon is way smaller than the weight of the truckload, because you need to integrate for this density for the volume. These two samples have different volumes, but porosity doesn't depend on the volume, so it's intense. It's an intensive property. I don't know if I make it clearer. Excellent. Okay, and normally these intensive properties are called specific because they depend on something. Normally it's the volume. So the typical example is density. Density is also called a specific mass, or it could be a specific weight if you multiply by by the gravity. So, well, here's the example. Density is the specific mass. So it's the limit if you take the derivative of mass against volume. If everything is homogeneous and you don't have much changes and you have a small sample, then this is a good approximation of this is the mass over the volume. So density has units of mass over length to the power 3, and typically can be expressed on grams by meter or grams by cubic centimeter. I'm sorry, kilograms by cubic meter, etc. Any measure of mass divided by any measure of volume. Normally, most engineering practices work on international units, international system units. So it's normally going to be kilograms or grams divided by cubic meter. But it could be something else. Could be stones by square feet or so. I mean, but it's not very, very common. And water, you might know this. A liter of water weighs 1 kilo, roughly. So a cubic meter of water weighs a ton, 1,000 kilograms. That changes slightly with the temperature, but it's more or less that. And since I work with seawater, salty water or ocean water weighs slightly more because it has salt. It weighs 1,025 kilograms per cubic meter. So it's a small difference, but that difference is enough to make a difference. Also, well, this density is a specific mass, and you can also call specific gravity the density of a fluid divided by the density of water at 4 degrees Celsius. So it's a way to say if things are more dense or less dense than standard water. But like I said, the density of water changes with temperature. The hotter the water is, it weighs less. It can even weigh when it's boiling around 960 kilograms by cubic meter. And you can see actually that it has a maximum around 4. Then it actually goes down again, and that's the reason why ice actually floats. I mean, ice. There's a more complex reason. It has to do with the restructuration of the water molecules into another bonding shape. I'm not an expert on that, but that makes the ice use a larger volume, so it has a smaller density, and that density, that difference in specific mass, is what makes icebergs and ice float on top of water, as you all have seen in glasses or maybe in the ocean. Okay, specific weight is nothing more than specific mass times gravity times g, right? And it has units of not mass but force over length to the power 3. So typical units are Newton divided by square meter, which you could write down as Pascal divided by meter, for instance. And in other unit system, it has other units. We don't go into there because, yeah, I don't think that's very interesting. But the typical value, again, is 1,000 times 9.8, so more or less 9,800 newtons per cubic meter. Which it's pretty heavy. Water is pretty heavy. It doesn't look like it, but it's pretty heavy, even compared to soil, which normally interact. If you're done soil mechanics, water is really important and in determining the mechanics of the soil. Okay, back to the initial condition, to the initial slide. One very important property of fluids is viscosity. Okay, and viscosity as we said, a fluid is a material that deforms under a shear stress, right? That's the definition. Viscosity is the tendency of that fluid to resist deformation. Okay, so the more viscous a fluid is, the more opposition is going to give to this shear stress. And we've all had some experience with that. We've all, I don't know, tried to scoop honey out of a jar, or dulce de leche or manjar, or I don't know, ketchup or stuff like that, which are very viscous compared to water, right? So you know that when you put a, I don't know, honey or ketchup or whatever, it will remain more or less the same. Okay, it will not drain, like we said before, and it will not yield. I want to emphasize something. This typical figure that you see here, when you have a thin layer of water and then a plate imposing a shear stress. This is an schematics. I mean, in reality, nobody is going around with a plate shearing fluids, right? The main mechanism for the shearing is actually the same fluid. Normally, the same fluid moving. Okay, so let me try to illustrate that. I'm gonna try to switch back. Let me see if I'm able to do this. Okay, hopefully the whiteboard more or less is visible. So again, let's say you have the ground under a slope. So this is going to be the ground, and it's going to have, let's say, an alpha slope. It doesn't matter. And let's say you have a layer of fluid flowing down slope. Okay. And this is something that you will typically see if you keep on studying hydraulics. So what's going to happen? I'm gonna make, this is really just in schematics. What's going to happen is that the water is going to flow more or less with a uniform velocity profile. Let me do this better. So let me just split the water, and more or less it's going to have a uniform velocity profile, and we're going to call this V. And if you remember, we said at the beginning that there is this no slip condition. So the water at the very bottom of the canal or this stream is going to remain stick to the bottom. So here the velocity is going to be 0. And here the velocity at the end of this boundary, we'll get into that boundary later on. Don't worry about that. But there is a boundary at some point in which you have a velocity, and then the water is flowing more or less uniformly. It's not exactly uniform, but for this schematization we can use. And what's going to happen is that you're going to have a velocity gradient. Near the bottom is almost 0, but here at this boundary is larger. Okay, and normally we're going to call this dimension, we're going to call it y, and this dimension we're going to call it x. Okay, and from this point on, I mean, upwards, the water has a constant velocity. I wanted to make this difference because normally you're going to see this plate moving, but in reality there are no plates moving. All right? It's the same fluid most of the time that's going to induce a shear stress. Okay, and that shear stress is going to induce in time a difference in velocities. At some point, because water tends to stick together, at some point you're going to have a large velocity, like here, and at some point you're going to have zero velocity at the boundary. All right, and this gradient here, let me just, and this gradient here, uh, you can actually compute the gradient. So it's dv over dy. Is a rate of the deformation. All right, is the strain rate. Strain is deformation. Strain is when you're loading a body, it will strain, it will deform. This is the strain deformation rate because water deforms continuously. So this deformation rate is going to be proportional to the strain, to the stress that's being applied onto the water. So the stress here, I'm going to put it as a tau, which is normally the name. So tau is the shear stress, and it's going to be proportional to this strain. This is key of the definition of viscosity and of fluid dynamics. So Mr. Isaac Newton, he figured that most fluids have a proportionality between these two properties: the shear stress on the one hand, and the strain rate on the other, and that the relationship, the ratio between those, that's the viscosity. So let me just write it down formally. So tau is normally assumed to be a mu, which is a proportionality constant, times dv over dy. This is a really key concept. And this proportionality, this mu, only holds true for Newtonian fluids. This is fluids that behave like, it's not ideal the name, but it's Newtonian. Like most fluids, water among them, behave like this. So the larger the strain, or the other way around, the larger the shear stress, the larger the strain that you're going to induce, but always with the same constant. And that constant defines the fluid. So you have one constant for water, another constant for any other fluid. Okay, let me go back to the presentation. Was that clear enough, or I mess it up a bit? I think this is very important, and I particularly, when I studied this, I found the plate example a bit vague. You don't normally see any plate on water, so what you need to retain here is that the shear stress is going to deform the water, and the way it deforms is dependent on the viscosity. Excellent question we have. What dimensions has tau? Well, tau is a stress, it's a shear stress, so it has pressure units. Okay, I hate to go back to the whiteboard, but I think is the best way I can show you this. Okay, let me. Okay, so we said tau is going to be mu times du dy, right? What units does this have? Tau is a stress, so it has units of pascals, or Newton time square meters. Then mu, we're gonna leave it blank. And what units has du over dy? Well, du has the same units as U, so this is meter per second, times divided by meter, right? So these are newtons over square meters, and these are 1 over S, right? So these are the units of mu. So the units of mu, I know this wasn't exactly the question, but I'm just hanging to it, is Newton over meter squared times seconds, or, oh, I block it, or sorry, well, Pascal times, I'm sorry the mess, but I'm gonna write it here. There's something going on in the corner. So it's Pascal times second, or Newton over meter squared times second. That's the units of mu, and it's important because it's the way you're going to compare how viscous one fluid is against another. Okay, I think I overran a bit the time. Let's take 10 minutes break, and I'll see you guys around in I have 17:25, so around 17:35. All right, see you then.
Oye, Tommy, ahora que estamos en recreo, vente a sentarte al lado mío. Piera, Piera, estamos sentados al fondo con el Tommy.
Okay, we're back. Hopefully you're all sitting where you should be sitting. Okay, so we finished before the break with this idea of viscosity, right? So you're going to have a something, could be a plate, it could be the same fluid moving, that's going to exert a shear stress over the flow, over the fluid. And that's going to deform the fluid, and that deformation you can measure it as a gradient in velocities. Since the fluid deforms continuously, it doesn't deform on units of distance, but it deforms on units of velocity. And the gradient of this velocity, the change, the vertical change of this velocity, uh, is going to be proportional to the shear stress that you're exerting. Okay, and that proportionality is going to be the viscosity. So you can think of viscosity as a property resisting draining or resistant strain, or is what is opposing the deformation of the fluid. And we normally going to see Newtonian fluids, which are fluids that have follow a viscosity law which is linear, right? So, for instance, fluids like water, alcohol, most gases, they are Newtonian. There are some other fluids that are not Newtonian. I'm sorry I'm skipping, but I think this should be here. Okay, and there are other fluids that don't work like Newtonian fluids. For instance, the toothpaste, right? If you leave the tap open, normally the toothpaste won't get out of the container, right? You have to squish it a bit. So we have a question. So higher viscosity means less draining. Yes, higher viscosity means less draining. So the viscosity of honey should be higher than water, right? And the viscosity of oil should be higher than that of water. Okay, and as you can see here, there's a straight line showing Newtonian fluid in which the shear stress tau is proportional to the shear strain, to the deformation. So it's a straight line. So if you measure, for instance, if you're able to measure in an experiment the deformation of the fluid and the stress that you're exerting onto the fluid, and you plot those points, they should follow a straight line. This is important, well, because it's a fundamental property, and also because you're going to have an homework about exactly what I'm talking about coming this Friday. So pay attention. There are other behaviors. Like I was saying, the toothpaste, it shows a Bingham plastic behavior in which you need a minimum shear stress for the fluid to start moving. If you, let's say you have probably all of us have seen an older toothpaste that you let it dry and it's all dirty, and you really need to squeeze it for the paste to start flowing. So in that case, the yield stress is higher. So you need a higher force to make the paste to start moving like a fluid. But after you pass this initial yield stress, then it behaves just like a Newtonian one in a linear relationship. There are other materials that show a behavior of shear thinning, meaning that the higher the deformation, the less opposition they offer. So I'm not sure, but I think steel, once if you load it very, very high, once it starts moving, it opposes less and less resistance. I'm not exactly sure about that example, so don't quote me on that. But there are materials that show that, and there are other materials that work the other way, and they're called shear thickening, meaning that the more you deform it, or rather the more rapidly you deform it, the more stress you need to keep on deforming it. I don't know if there is a typical example that you can try at home. Is if you take how it's called? It's something like flour. It's called maizena. I don't know the name in English, but if you take maizena and corn scratch. All right, if you take corn scratch and you mix it with water, it depends on the exact combination. But if you make a fluid with that, it will behave like a shear thickening fluid, and we can look for an example right now. This is one of the cool things of the internet that maybe when I was studying, we didn't have that. You needed to actually somebody come and give you the right video in a floppy disk, but now you can just Google it. Non-Newtonian Newtonian fluid. You can look for examples, and it's really cool. Actually, there's a classic example when you put this mixture into a speaker. So let me show you. Are you seeing it? So basically, here some people put cornstarch onto a speaker, which is just a mixture of cornstarch, maizena, and water. I don't know exactly the same amount. You can look it on your own. And they turn on the speaker, and it's really cool because actually you can see these fingers going out, because you know the vibration on the speaker, they have certain patterns depending on the frequencies you're moving. So there are parts that are experiencing a very heavy shear stress, and that parts of the fluid are getting really stiff. Okay, you can try this at home, and actually if you make enough and you put it into a bowl, you can try punching it, and despite what you can expect, you're not going to spill. Actually, it's going to behave like a really solid thing if you do it properly. All right, so this is a classic example of non-Newtonian fluid. Okay, we're not going to be seeing many of these in the course, but it's important that you know that they exist. Okay, back to the presentation. And here's what was being asked recently. Here's a classic example of if you have shear stress in the y and the shear and strain on the x, you're going to have one straight line for each Newtonian fluid that you have. So, you can see the hand, right? Yes. So for instance, here you have oil, and the slope, or the inverse of the slope, represents mu, or the dynamic viscosity. Here you have water at a certain temperature, and you can look it up. But if you heat up water, it is less viscous. Okay, the more heat, the more temperature it has, the less viscous it is. All right, back to where we left off. Okay, so viscosity is the position to the deformation again. The exact way in how this happens is not important to us engineers in this course. You can look it up, but it has to do with the attraction and the random movement of molecules. So it's a chemistry stuff, but the important thing is that it exists, and we can model it as a linear relationship. And why is this important? Because if you know the exact stress that you're putting into a fluid, and you know the viscosity of the fluid, you're going to be able to compute the deformation, and the velocity of the flow will depend on this deformation. Okay, and like I said, if you look here at water, the more temperature it has, the smaller the value of dynamic viscosity it is. For air, for instance, it's the other way around, although it's a very stable or almost flat curve. For glycerine or other oils, it's the same. The more temperature it has, the less friction it gives. This is why, in your car, you need a certain oil because to smooth the movement of the cylinders, because that's going to be very, very hot. So you need the oil to be able to still give protection to the friction at a very high temperature, right? So I went beyond me on this, but these are the units of dynamic viscosity. So it's a stress divided by the deformation strain. So the stress is measured as a pressure. This could be pascals or Newton per square meter, and the deformation is measured on 1/time. So you can arrange it like that, or you can arrange it as Pascal per meter. This is Pascal per. I think there's an L. Yeah, this L here is not right. I'm gonna look it up. All right. Oh, sorry. This is mass. This is not force. Yeah, in mass is kilograms per meter per second, or you can think of on this as Pascal times second. It doesn't matter as long as it is consistent. You probably saw that part on the book on consistency of the units. It doesn't matter exactly the value or how you're expressing units, but it has to be consistent. Yes. So just keep that in mind when you do computations. Otherwise, you might be making very, very big mistakes. Okay, and this is just a side note. If you divide the viscosity divided by the density or the specific mass of the fluid, you get what is called the kinematic viscosity. And it's cinematic because you remove the mass from it. It's only velocity. And this is important, for instance, when you want to talk about turbulence and mixing. Normally, both things matter, viscosity and density, so you can combine them into one parameter. And for those of you who may later study turbulence behaves similar to a kind of viscosity. So this is a way to put everything into the same framework. For us in this course, this is just a viscosity that doesn't take into account the density. Okay, so you can compare it between more dense and less dense fluids. Okay, so that and here are typical values of density or specific mass, dynamic viscosity, and kinematic viscosity. So you can see typically we're going to be talking about fluids in the range of 10 to 20 degrees Celsius. So normally density is around a ton per cubic meter or around 1 kilo per liter. Viscosity is in the order, you don't have to memorize these values because you can always look them up, but it's in the order of 1 to 10 to the minus 6 for the kinematic, and 1 to 10 to the minus 3 for the dynamic. Okay, with the right unit. So this is Newton. You see, here it is expressed as pascals times second. It could be expressed in some other unit. And here, the dynamic, that kinematic viscosity is expressed as meters squared times seconds. So you see, you don't see any mass here, any force. So this is only velocity related. Here we're talking about forces. Okay, that's why this is dynamic, and that's why this is kinematic. Okay, and these are reference value for air. Again, you don't need to remember this by heart. It's interesting though that, well, air is a lot less heavier than water, and a lot less viscous, which is expectable. But it's a bit more, or actually tenfold more, kinematic viscous, right? Because it weighs a lot less. So kinematic viscosity lets you compare across viscosity and the effect of viscosity and the effect of density. All right, before we move on, let me go back to I know this has been a bit messy, but let me go back to the tablet, and let's do a small exercise. Okay. So there's an example in the book, and I think you've probably seen it, but I think it's important we can discuss it a bit in order for to better understand this concept, and to lose the hand a bit in how you're doing this kind of computation. So the example this says like this. Let's say you have a tube, right, of water. There's water flowing in, and you have a vertical velocity profile. Okay, this is not very nicely drawn, but you get the idea, right? And this represents the velocity u, and the vertical coordinate, we're going to call it y, just like always, but we're going to measure it from the middle of the tube. So we're going to call this y. Okay, and let's say you have a velocity profile that is given to you. So u, it's 3v. Sorry, yeah, my handwriting is not the most beautiful, and this tablet doesn't help much, but please bear with me. 1 minus y over h. Wait, let me draw this just a bit more. Okay, so like I said, u is 3v over 2, y 1 minus, and this is square. Okay, so this is u. Okay, so what this tells you, there's two things that I want you to follow here. Basically, well, and the question is, let's compute the shear stresses, the internal shear stresses, and in which part of the flow the shear stress is smaller. That's the question, and you can see actually the example on your own. But what I want to stress here is that the viscosity of the flow is going to determine the velocity. Okay, and you can think of viscosity as layers of flow. So let's draw here a thin layer, and viscosity is going to exchange momentum of this layer to the layer below, and vice versa. So the same idea, if you have a plate moving on top of a fluid, the plate, the viscosity exchanges the momentum of the plate with the layer below, and then that layer below exchanges momentum with the layer below, and so on, up until the bottom. So what viscosity does is that it exchanges momentum in the normal direction of the flow. I'm sorry, in the tangential perpendicular direction of the flow. So if the flow is flowing to your right, viscosity is going to exchange momentum up and down, and that's what's doing here. So it's not that you have a velocity profile; it's that the viscosity determines this velocity profile. You have a it's a positive feedback between those two. Okay, and I think that's not very well explained in it's not normally well explained. Okay, so if we want to compute the distribution of shear stress, what we do is, well, we know this is water, so we know that the shear stress tau is going to be equal to mu times du over dy. And since you all know calculus, okay, this is mu. We can take the constants out, right? So it should be 3v over 2, and the derivative of the inside part should be minus y to h. And here I forgot, but h is this distance. This is h. So this is the center line. All right. Is this right? Yeah. So basically here you can see this is mu. Let me just, I'm sorry, and this is square, so this is square. And here the 2 is here. Okay. So basically this is mu, this is minus mu 3b h squared times y. So it's basically a constant times y, right? And what this tells you is that, let me see if I can move this. Yeah. What this tells you is that if you have your y as an axis like that, and you compute your velocity, so your velocity is going to be a parabola, something like that, and your tau, so your stress is going to be a linear thing. And this is okay, so this is y, and here you have, this is u, and this is tau. Okay, so you can do this kind of computations, but the important thing is that you realize that what the viscosity is doing. Viscosity is exchanging momentum, and is exchanging velocity. I mean, if you have one layer with a larger velocity than the layer before, that's gonna, viscosity is gonna induce a change of momentum between the larger velocity and the lower velocity layers. And you're gonna have a maximum tau when this change in velocity is larger. When you have two layers of equal velocity, which happens here at the lower part, your tau, your shear stress is minimum, is 0 actually. So if you have two layers, if you run your hand over water at the same velocity of the water, then you're not going to exert any shear stress. You need a difference in velocity in order to viscosity to induce a shear stress. All right, let me save that. Back to the presentation. Any questions so far? Okay, let's move on to pressure. Okay, like I said before, pressure and shear stress are and pressure and shear stresses are both stresses, and they both represent internal forces, right? And the pressure is the limit of a force over an area. You all know this from previous courses, and pressure it expresses in units over square meters or pascals. Normally, depending on the units, we can talk about kilopascals, megapascals, gigapascals, etc. Because normally 1 pascal is a very, very slow unit, a small unit. I mean, if you think about 1 kilogram over 1 meter, you can barely feel it. So if we're talking about water, like I said before, water is a very heavy thing. So in order to have 1 kilo over 1 square meter, you would need a very, very small amount of water. You can compute it, but it's really small. And instead, if you have a cubic meter of water, you're going to have a ton, which is 1,000. Let me see, it's 1,000 newtons, so it's going to be 1,000 kilograms times g, which is more or less 10. So 1 ton is over 1 meter is going to be 10 kilopascals. I might be missing a 10 around there, but the point is that normally 1 Pascal is a small unit. So normally you will read stuff in the order of kilopascals, megapascals, gigapascals, etc. And the pressure acts on normal to the surface. Okay, so if you have if you stick, let's say, a board into the water, you're gonna have pressure normal to the board and no tangential to the board. One other interesting stuff of pressure is you can talk about absolute pressure, but that is a weird concept because, as you know, here on Earth we already have a lot of pressure due to the atmosphere, and you can measure that. I mean, 1 atmosphere is a certain amount of kilopascals. You can look it up. But normally we don't mind about the absolute pressure, but the additional pressure from starting from atmospheric pressure. So it's normally pressure is normally measured against a reference point. So when you say your tires have 33 psi, is 33 psi on top of the atmospheric pressure, right? So, okay, here are the values. So 1 atmosphere is more or less 101 kilopascals or 14 psi, etc. And the unit I like most is 10.3, but you can think on 10 meters of water. 10 meters of water. Here it says MCA, which means metros columna de agua. So if you stack 10 meters of water, you reproduce the same amount of pressure that the whole atmosphere has on top of you. And normally when we're going to see throughout the course, but normally we can express pressure in meters of water because we know how much water weighs. Okay, so we'll normally within the fluid, we're going to talk about relative pressure, relative to the atmosphere. We don't normally mind much about the absolute pressure. But if we would like to measure to an absolute zero, that absolute zero is the vacuum, which is, outside the atmosphere, and then you would need to add to your values the atmospheric pressure. As you know, the atmospheric pressure changes from location to location. It depends mostly on geography, but it also depends on the weather. So here in Santiago, for instance, we are at 500 meters above sea level, so we have a slightly smaller pressure than in Viña del Mar, for instance. And if it's raining or if it's going to start to rain, then you're going to have a drop in pressure. So in order for us not to mind much about that, we normally talk about relative pressure starting from the free surface of the fluid down. Okay, here's an interesting and a relevant concept for us related to pressure, which is the vapor pressure. I'm sure most of you have heard about this, but the vapor pressure is the pressure when a fluid passes from the liquid phase to the gaseous phase. All right. Normally, and this happens for several reasons, but the typical example is that, as you know, water is actually a mixture of molecules. So there is no continuum of water. There's water, and everything else has a lot of voids in it, right? When the pressure is too low, you allow this small voids to grow larger. Yeah. And as they grow larger, normally what happens is that they're going to grow and then become unstable and then collapse onto themselves. You've all seen this. For instance, if you boil water in a pan, in a kettle, or I'm missing the word now, but if you boil water, what happens is that you're making you're reaching the atmospheric pressure with the vapor pressure of the fluid. What you can see here is that vapor pressure normally around a standard atmosphere is around 0. It's not 0, it's above above 0. It is a really small amount above 0. But as you increase the temperature, the vapor pressure increases, and once it reaches the pressure of the ambient, the water will start boiling. I don't know if any of you have cooked into the mountains, but actually the water there boils at a lower temperature. It doesn't boil at 100 degrees because the atmospheric pressure on the mountain is lower, is around here. So the water boils before it boils. Well, it depends where you are, but it boils at around 80, 90. Okay, but what does the vapor pressure has to do with us besides cooking? Well, it is important because pressure can drop not only because of temperature, but can drop also because of velocity. We're going to see later on the course, but there is a relationship between velocity and pressure. What you need to know now is that at higher velocities, fluids tend to drop their pressure. So, for instance, here you're seeing a turbine, sort of, and at the tip of the turbine, you have very high velocities, and there you can have local cavitation. It's called cavitation is when the fluid reaches a pressure as low as the vapor pressure. You might have heard cavitation also in all houses in the plumbing, when you open the faucet and you hear all the plumbing clanking, because there is a sudden increase in velocity, and that velocity reduces the pressure, and the system is not well designed. So there are parts that have already very low pressure. So when you lower the pressure further, you reach a cavitation point. And cavitation can be a problem for structures, can be a problem. It actually induces stresses and forces. So it is something that has to be kept an eye on. Also, when you design later on, if you want to design a pumping system, you need to be mindful of cavitation. You can't drop the pressure below the vapor pressure, because your system will start to create bubbles. Related to pressure, we have the bulk modulus. We said at the beginning that we have two types of fluids, right? We have liquids and gases. And the main difference is that liquids, you can't compress them. To put that into a more formal definition, you have the bulk modulus. And the bulk modulus tells you how much a change of pressure can change your volume as a relative value. Okay, so if you increase the pressure on the fluid, how much the fluid is going to compress or expand. And then the formal definition is this one. So a change in pressure, how much change on relative volume it changes. So you see it's delta volume times divided by volume. So it's a relative change in volume. And since volume is the inverse of density, you can also express this with the specific mass, rho. So the change in rho over rho. Okay, so a large value of bulk modulus indicates that specific fluid is very, very little compressible, and a small value means that you can compress it easily. Okay, and we get to the final. Before that, there is a really cool thing that the bulk modulus tells you how much you can compress a fluid, this being water or air, and also has to do with the velocity in which these perturbations move through the medium. So let's say I'm sure most of you have seen this terrible accident that happened in Beirut. Probably most of you have seen the shock waves from it. I I don't know if for anyone is a sensitive topic, we can just pass it over. But if you want, you can look videos on it, and actually you can see a almost perfectly round shape of a pressure wave moving through the air. Uh, and the bulk modulus, among other properties that is not really interesting to get into, determine the velocity of which this pressure is, in this case, is not a pressure drop, but a pressure increase travels. And I'm gonna leave it to you to if you want to look at those videos. But there is one video that I want to show you, and is that you can actually model how this pressure wave behaves. So probably you've heard about there is one area of hydraulics which is called computational fluid dynamics, in which you can model the fluid with all these properties, and in particular you're modeling the pressure. And again, the explosion here in Beirut, you can model it as a sudden increase in pressure, right? And you can model how that increase propagates. So here I'm showing the results from a group of researchers, and they model this huge increase in pressure with the topography of the port. And here in the scale is the velocity at which no, it's the peak over pressure. So you should see several interesting stuff. You could see that the velocity of the propagation is more or less uniform. Because as I understand it, I might be wrong, but as I understand it, the velocity is a property. I think this kind of shocks propagate with the speed of sound and not faster, but I might be wrong with it. And you could see, for instance, if we stop in here, you can see this increase in this overpressure. Here it doesn't say the units, but if you've seen the videos, you've seen glass being shattered and people falling. So there's a huge increase in pressure in the buildings near the explosions, and even several kilometers far away. Here I don't have an exact dimensions, but I know the blast hit a very large area. So this has to do with the compressibility of air. Since air is able to compress, you can create this kind of thermic bombs that depend on this huge increase in pressure. You can't have this large increase in pressure in water. I mean, you can, but not with this magnitude. And also shocks propagate in water, but at a different velocity, which is determined by the properties of water. All right. Okay, we're getting into the final part of the class. So when we return, I want to talk about two things: surface tension, which is the final property of fluids, and I want to tell you about the homework that we're going to be sending on Friday. So let's take a 10-minute break and see you guys later on. Okay, hopefully everyone's back. All right, let's get into the final part of the class. The final property that we want to talk about today is surface tension. Okay, and the surface tension is different from viscosity. So you shouldn't try to mix it with that. And surface tension is a force, is a resistance that the fluid has on the surface, on the boundary between the fluid and some other fluid, for instance, air. Okay. We'll see later on, but here the typical example is there are some insects that are able to walk on water. You've seen them, the water striders, or some kind of, I don't know, small insects are able to step on water because the boundary between the water and the air has some small tension. Okay. Again, the reason why this is, you can look it up in more details. It has to do with chemistry between the molecules of the fluid, but it's not really very important for us. The thing is that there is a force that works on the surface of the fluid. So again, the details are not very important, but it's important to understand a few differences. The attraction between the molecules of the same fluid is that force is called cohesion, and the attraction between different molecules, between the fluid, for instance, and a boundary, is called adhesion. Okay, it's the same. For instance, you probably know that the raindrops are not really clean water because as they fall down, they attract, I don't know, different pollutants that might be in the air. That attraction happens because of adhesion. So small molecules stick to the water. Okay, but at the interior of the fluid, cohesion forces are the ones that create this force at the boundary, at the surface. Okay, and the surface tension is a bit different from the forces that we've been talking about, because it's a force per unit of length. It's not a force per unit area, it's a force per unit length. So it depends on the length that it acts on how it works. Here is a typical example. So let's say you have a water column within a small pipe, and you have adhesion between the water molecules and the pipe walls, which might make it stick to the walls. And you're going to have this shape here, and this shape is going to be kept by capillarity. There are going to be forces in this boundary. They're going to be pulling up the rest of the molecules. Okay, so you can think of it as a, for instance, here you're putting a Lusaplast on top of a bowl, and the force that this plastic exerts on the contents of the bowl is similar to the surface tension. Okay, and like I said before, here it is important is a force applied over a length and not an area. So for instance, if you see a drop that is keeping its form, is because at the boundary you have the surface tension that is keeping it together, and the surface tension is similar to the weight of this drop. This is important because, as you can see here, you've all seen water drops, and they're small, right? And they are small because if a drop is too large, it will break down into smaller drops. So that gives you an idea of that the surface tension, it is a small force. It's small for any practical application, at least for engineering purposes, but it's a force that it is there. So it is important for small distances and small weights and small forces. It's only noticeable under small forces. Okay. So before going to that, let me show you a really, I think, it's a cool example of surface tension. Wait. Okay, so probably you've seen this guy. He's an astronaut from Canada. I can't remember his name. Maybe he's yeah, is Chris Hadfield. He's a very famous astronaut, and he was asked by a group of people to perform an experiment on space. So I don't have the volume here, and I'm gonna tell you the experiment because it's really cool. Here he's taking a cloth, just a regular, something like a towel, a small towel, and he is pouring water into the towel. So the water is normally in this kind of bags that has a seal in the entrance. So now he's opening the bag and actually letting the fluid go out. First, realize that the water is not flowing anywhere, because here now he's at the space station. There is almost no gravity. There's microgravity, so the water doesn't flow down, and it tends to stick together in a much larger drop that you would see back on Earth. Because for any practical measurement, the water here is weightless. It doesn't weigh. So the only force that holds it together is the surface tension, which normally on Earth is a really, really small force. But here on space, it starts to be more important. Okay. And now he starts spilling, but forcing to spill the water onto the cloth or onto this towel. You see that, right? So the experiment is they are asking, now the towel is soaking wet. And the question was, what happens when you, what's the word? When you grind? I don't know. When you try to dry the towel, by tossing it in space, twist it. Yes, thank you. What happens if you twist the towel? You can see the droplets going everywhere, right? So before that, probably some of you have seen this. What do you think is going to happen? Here on Earth, you twist the towel and all the excess water falls down, right? What can you expect here on the space station where gravity is really small? If you've seen the video, you know the answer, but maybe you can have an idea beforehand, because we're talking about surface tension. Okay, so have a look. Okay, I think this is really cool. You can see the water coming out of the towel because he's forcing it out by twisting the towel. And then the water sticks around the towel and it sticks around the hands of Chris, right? And this is happening because surface tension is actually larger than the other forces in play. There is no weight. There is no pressure, so surface tension dominates. And this is, for normal applications, this is very weird. It doesn't happen that much often, okay? So water sticks together because of this tension. Unless, if he would move, if he would shake his hands or the towel, then water will go away because the acceleration of the hand will be larger than the surface tension. But since he's not doing it, then surface tension dominates. There's also an anecdote of the same astronaut that he was doing a spacewalk. He's just, I don't recall if he was latched to a cable or just moving with this jetpack. But then one eye starting to drop water, to cry, let's say, to lacrimate. And normally it wouldn't matter, if you have an eye that is dropping tears, you don't mind, you just rub it down. But now he had his helmet on, so he couldn't just move his hand around the eye. And water started to accumulate because water didn't drop. So surface tension created a film of water onto his eyes, I think both eyes, and he couldn't see a thing, and he couldn't do anything. So surface tension can be a real menace. Of course, NASA, they're very clever people. They had actually a manual to how to deal with that, and they told him, I don't recall exactly, but he did something so the tears dried or something. But this is just to highlight two things: the surface tension exists, and the surface tension is really small. You need to be in space for it to be relevant, or you need to be in the right environment. For instance, let me show you. Let me get back to. Okay, so when or where is surface tension relevant? I'm gonna skip this. Is important in the behavior of soils. If any of you have studied soil dynamics or soil mechanics or groundwater, the surface tension creates a force called capillarity, which is the force that drives the movement of water through these very small voids that we talked about at the beginning. And capillarity happens because, let me just go back. Capillarity happens because the space, the tubes where the water moves is so small that actually surface tension can overpower gravity or the other forces in action. Okay, capillarity is only effective in very small diameters. For instance, in your veins, capillarity is a very important mechanism of how the blood flows. The blood is also a fluid, and it's a very viscous fluid. So viscosity and capillarity are very important for how the blood moves through your body. Okay, and like I said, in soils and water in soils, capillarity and surface tension is important. And in your blood vessels too, stuff like that. We're very, very fine, very, very small channels or tube where the water can flow. So this is not important for the course. Just to give an idea that you probably know, in the ground there are zones that have saturated water, meaning that all the pores are filled with water. And if you have a space with pores on top of a space with saturated water, these small pores are going to induce capillarity, and they're going to start sucking up water against gravity. So if you put a wet soil and you put on top of that a dry soil, that dry soil is going to draw water from below. If you have plants in your house, you probably have seen something like that. You don't need to put water on every part of the plant. You can only put water on the bottom, and the water will flow up, right? And that movement of water is dominated by capillarity. That's the main idea there. It happens also in constructions. So for instance, if you have a brick wall, the brick has also pores, and through capillarity, water is going to start to seeping in. It's going to get into the wall. But you can there are ways you can insulate your walls and your infrastructure. I'm not an expert on this, but the main idea is that if you have small spaces, then capillarity might be important and might start sucking up water. Okay, and this is a picture of a water strider, which is the insect that I just told you before. And here is a value, it's a typical value of surface tension of water. It's about 0.07 newtons per meter. Okay, so it's a very small value. Here, by comparison, you have another value for mercury, which is an order of magnitude larger. So I'm gonna leave you an idea. You could compute, for instance, the weight of this spider, knowing that it is stepping on 6 points, and having an idea on the angle on of the surface that the legs of the. Let me just silence you. I'm sorry, Joaquin, were you going to say something or? Okay. If you have an idea of how the surface is deformed by each of the legs, yeah, go ahead.
Okay, I would think that surface tension is esta medida
Yeah.
Newton slash meters, like in area, Newton.
Yeah.
Area.
No, that
with meters.
Yeah, good question. That's exactly the point that I wanted to make. The surface tension is measured on newtons per meter, so it matters on the let's say on the diameter rather than the area that is acting. Okay, so it's different from the previous forces that we saw, which are normally pressures or stresses. Surface tension is a force per unit length, so it's different, right? The exact mechanism of why that is it probably has to do with chemistry and bounds between molecules. I'm not really sure, and for all practical matters, it's not very relevant. It's only important that it depends on the actual length on which it is acting. Okay, and for instance, here in the water stride, it depends on the length on the of the legs touching the water, and the direction of the surface will tell you in which direction the force is going to be applied. So you see this bag, the water strider, it needs to deform the surface for the water tension to work. All right. Of course, any fluid with a larger surface tension module, you will need to deform it less, and you will need to apply it over a smaller length in order for it to create force. But since this is water, well, only very, very small animals like this guy here are able to step on water. Or maybe you've seen, if you throw, let's say, a leaf on the water, it's also surface tension that is avoiding the leaf to go under. So again, this is to illustrate this. Let's imagine that you have a drop, right? A drop of water. Then surface tension works around the line, and then you cut your drop by half. Then surface tension works around the line of the drop. So here the area. Let me see if I have it here. No, I don't. Let me just go back to the whiteboard to see if we can sketch this. Okay, so if I try to draw what's there, basically you have a drop of water. Oh, okay, my pulse is not the best today, but you get the idea. And you have this drop that is cut in half. So along the boundary, you're gonna have surface tension acting, right? And in the bottom, I mean, in the drop, you're gonna have the weight working down, right? So the weight is going to be equal to gamma times the volume, right? Gamma is rho g times the volume. And the volume of a sphere is, don't recall it by heart, but is P. Let me just Google real quick. Volume of a sphere.
Es 4/3 pi r cubo, creo.
Yeah. Yes. 4/3. Let me just move this so I don't run out of space. So this is gamma 4/4 p, yeah, r to the 3, and we're going to call r the radius, right? So let me just draw this, and this is r. This is r, and this here is sigma. Okay, so that's the weight. Okay, and the force up we're going to call force sigma. Let me draw the sigma right. Is going to be sigma times the perimeter. All right, and the perimeter is p times the diameter, 2 times r, right? This is right. And if this is true, then these two should be equal. So we're going to have sigma. So you see sigma is acting on the line. So sigma has units of Newton times distance, and we're multiplying this by one distance, which is the radius. So this is p to r, and this should be equal to gamma 4/3 p r to the 3. So we can
But you're considering
take those
the whole
down.
sphere.
Sorry, what?
But you're considering the whole sphere, and it's half.
Yeah, you're absolutely right. This is half, right? So this is okay. Yeah, you're absolutely right. This is 2. Because this is an internal force. I mean, the full drop is going to be dropping, right, from the sky. So there is no force to keep it from falling, except from, you know, aerodynamics and stuff. But internally, or not internally, on the surface tension is keeping this drop together. And you're right, this is only the half. And if you cut it in a different position, that's actually a very good comment. If you cut it in a different position, let me just draw this on a different view. So we're cutting this thing here by half. And here's the value that I'm just saying, right? Oh man. Okay, but if we cut it here, what's going to be the value, right? So if you cut it in a lower position, the circle, let me just draw the circle around, is going to be smaller, right? Because this actual radius is smaller. So the length on which the surface tension is acting is going to be smaller, and also is going to be acting in this. Let me just draw it here. It's going to be acting in this direction, in the normal to the surface. So, and then you can decompose it on a vertical and a lateral force, right? Only that here at the medium point, you only have vertical force. The lateral force is 0. So it's a very interesting question. And of course, at this point, you should be balancing out the weight at that point, right? So it's a very interesting question. So this is just to make the case that for surface tension, it is important the length on which it is acting. And from here, I'm sorry the mess. I mean, this is not my best handwriting, but from here, you're absolutely right. This should be half. And from here, since we know sigma, because you can look it up at on Google or stuff, you could get a reasonable value for R, and should give you something in the order of millimeters, right? Because we know that there are no drops in the order of meters, at least for water. So this simple balance can give you already an idea of the order of magnitude of the process we're talking about. All right. I will post these scribbles. They're not the most ordered ones, but yeah, for the ordered one, you can read the book. I mean, the book is pretty neat, but this is just to help me convey the ideas, right? Okay, so we're approaching the end. And here's actually a small exercise that you can find also in the book. I'm not going to go through this because it's just repeating the same. But basically, if you have a tube and you stick it in and pull it out of water, like here, for instance, you're going to have capillarity effects here at the boundary. Here, the adhesion to the walls is important, and so water is creeping in. And you can compute this height by balancing the weight of what's inside the tube by the force that the surface tension is doing at the top. I don't know if you want to do this, but it's really similar to what we just did. And here in the other example, this is to be done with mercury. We have the opposite thing. So here the surface tension is stronger than the adhesion to the walls. So when you stick this tube, actually the mercury doesn't go up, and the difference which it doesn't go up, here's an extra pressure. You can think here of an extra pressure as the weight of the mercury that is missing here is being balanced by the surface tension here, given the right angle. And you are given the angles, and you are given the specific mass. So and you can see how this changes for different diameters. All right. It's a very simple equation, the same that we just wrote down, where basically the weight is being balanced by the surface tension around the circle of this tube, right? Projected by the right angle, right? And if you write that down, you should see that the smaller the diameter of the tube, then the longer the fluid can go into, because the effect of the surface tension should be larger. But I'm going to leave that to you, and maybe we can just review it next class. Okay, so that's the final diapo slide. So before we go, again, there is a couple of, I think, 1 hour left for the quiz for those of you who haven't done the quiz yet. Should be really straightforward after reading the book or after coming to class. I'm not going to have quizzes all classes, but I'm going to try to keep you busy with quizzes and homework almost every class. I'm going to try, but I can't really commit to that. But that's most likely the case. So be sure to be looking into the announcements. Like I said at the beginning, I'm going to post the link to this Google Meet. To this Google Meet, so it's easily findable for anyone. Are there any questions before we move on to the final part? Could be about the course, or could be about what we just talked about, or about any other thing. Yeah, I'm going to upload all the material. So the slides are going to be up. I'm going to set a page with all the videos that I showed, because you can't see them in the PowerPoint, and all the scribbles that I draw into this improvise whiteboard. I'm going to put them also, but I don't know if they're going to be very, very useful, but everything is going to be there. Of course, you can always come back and rewatch the video. Yes.
Is it possible that you could upload the presentation before, like at the start of the class, so we can take notes in the same PowerPoint?
Yeah, it's a good comment. Yeah. I'm gonna start. Yeah, it's a good comment. Let me just write it down.
Great. Thank you.
No worries. Okay, so I'm going to start uploading the presentation just before the class, right? Half an hour, a few minutes before, so you can have them and maybe write on top of that. No worries. I have another question. ¿Va a haber una guía o los ejercicios libres son suficientes? That's a good question. You should try to do the exercise of the book. You should try to go to the recitations, which, by the way, this Thursday is the first one. You should try to go to that. Of course, it's not mandatory. Coming to class also is not mandatory, but it's highly encouraged. You should go. If you can, make the time and go, especially if you're at home and you just need to connect. So try to go. In class and in the recitations, we're going to do exercises, and there are the exercises on the book. There is a high chance that we might ask you one of those questions or exercises in the midterms. So if you have done all the exercises in the book and all the exercises we see here in class and in the recitations, there is a high chance that you are going to have already one question ahead in the midterm. I'm really not trying to. On the other hand, I mean, if you only read the book and you understand it very, very well, you don't need to come to class. You don't need to go to the recitations. Should be enough, as long as you're able to, answer different questions from those of the book. We're not gonna do trick questions. I'm not gonna ask you stuff that I only mention in class. So it should be very, very transparent. I'm looking also at the maybe you can see it. The Mecánica de Fluidos de Bonifacio Fernández, which is a very cool book. It's in Spanish if you want to read it. It has a lot of exercises, and this is the book that I use when I studied. So since I have it, I'm also going to. So we're going to try to give you exercise so you can do on your own. And also we're going to do exercises in class and in the recitation. Here in this class, I only did a couple, and I had another that I could have done, but I think it was enough. And yeah, just to finish that idea, if you think that we're doing too few exercises, just let me know and we can do more. Okay. So, okay, the first recitation is this Thursday. You should go because we're gonna do a couple of exercises related to viscosity and how it is measured in a practical way. And on Friday, I'm gonna give you the first homework, and it has to do with code. And you're going to have to modify a Python routine to compute viscosity. Okay, so if you go to the recitation, you're gonna be in a good foot to start the homework. So in the first class, some of you told me that you didn't know about Jupyter Notebooks. So here's the thing we're going to be using. We're going to be using Colab from Google. I don't know if you know it, but it's basically just a Jupyter Notebook online. Okay, so if you go to colab.research.google, you're going to be presented with this page in which basically you can look at the welcome to. It's called Colab because of collaboratory. you can see several examples, or you can do a new one. Okay, in this case, we're gonna create a new notebook. And a notebook is nothing more than a lot of cells that execute Python code. Okay, so I understand that all of you know how to code in Python, so this is just to show you very briefly. So if you this interface is basically a Jupyter notebook that you run on Colab. So let's say you do your typical import. You import NumPy as NP, and then you execute that cell. You can execute it by clicking here on execute, or running the cell, or you can execute it by Shift Enter. Doesn't matter. And then you can do all the things that you normally do with NumPy, like, I don't know, random, normal. You create a random normal variable. And the cool thing is that this shows you the help of the function. So if you put log 10 scale 1 and size 1000 or 500, it will create 500. We're going to put this into a variable. It will create 500 values of a normally distributed function. And you can see var here, for instance. And you could, well, it's a very long thing, but, and you could, for instance, plot this. So for plotting, you're going to need, I don't know, Seaborn. I don't want to take too much on this, but this is just to show you that you don't need to install anything. You don't need to run anything. Then you can use this plot, for instance, for var. Need to show you a distribution. And as you can see, it is centered around 10, and it has a scale of around 0.1. I think it was the value. Okay, so the homework is each one on its own. Because I think it's not very, very difficult. So what you're going to have to do, I'm telling you this beforehand, you're going to have, I think it's a 2-hour limit since you start the homework, okay? Should be more than enough. What you're going to have to do is you're going to have to open one of these Colab notebook. And as you can see, oh, here on my own account, but if you choose your UAndes account, you should be able to do, well, exactly what I just did, and then save the notebook onto your Google Drive, right? So what you need to do is take the notebook that I am going to upload. It clearly says the parts that you need to fill in. There are a couple of parts in which you're doing a computation, and it is clearly marked with comments like modify from this line to this other line, right? So you need to do a couple of computations and modify those parts and then run the notebook. Okay, this is the first time that I'm doing this, so be patient. Let me know if how it works. And then that notebook that you're going to create, you can save it onto your Google Drive and then upload it as a response to the homework. The homework is going to have the same quiz format. I'm being asked when is this going to be up? It's going to be this Friday, and you're going from Friday morning, like, I don't know, 5 in the morning. So all Friday, and you're going to have all Monday up until the beginning of class to turn it in. Like I said, you're supposed to take an hour, maybe half an hour, especially if you go to this Thursday recitation, because you're going to have exactly what is that you need to fill in this function. So okay, just to summarize, this Friday I'm gonna put online the test. Okay, the test is gonna be the description of the test is gonna be there. And what you're going to have to do is open this file in Colab, modify it as it is asked for you to modify it, then save it in your drive or whatever you want, and then you can upload it in Canvas. I think that you can upload directly from your drive, and that's why I'm suggesting you to save it on your drive. But you can save it on your computer and then upload it whenever you want. I haven't tried this on my cell phone or on a tablet, so I don't know if it works. So I suggest you do it on a computer. If you can't, let me know, and maybe we can see if it works good in a tablet. You're gonna have time until Monday at the beginning of class. I don't want you in class, you know, finishing the homework. Okay, so I'm getting more questions. No, sorry. I'm being asked if we're gonna have 2 hours or the entire weekend to do this. You're gonna have the entire weekend. You're gonna have from Friday, Saturday, Sunday, and Monday up until 4:30. What you're gonna have 2 hours is once you start your homework, the homework closes in 2 hours. It's the same as the quiz. The quiz had, I think, 10 minutes limit, but you could have done the quiz, you know, whenever you want. So once you start your homework, you have to finish it in 2 hours, and I think that's more than enough. It should be enough time. But you can start your homework whenever you want. Start it Friday morning, and ending before the class. So be sure to start. I mean, if you start at 4:25, there is a chance that you won't be able to finish in 5 minutes, right? So take your time, take all the precautions you need. Like I said, this is the first time that we're doing a coding exercise. I think should work relatively well, but I'm open to criticism, so let's see. Okay, any more questions about the homework? This is a very good moment to ask them. No? Okay, my email, you can, I think it is on, let me just be sure. Yeah, my email is on the homepage of Canvas, but I can copy it here. It's bcarrion@mibandes. Yeah, and you can send me any email you want. I think I said it at the beginning. It doesn't have to be in English. If you want to write it in Spanish, no worries. If it's a question relevant to the rest of the class, I take the freedom to post it on the discussion forum or someplace else. If it's something personal, of course, I won't do it. But I really encourage you to use the discussion forum. I don't know, if you have a doubt on the homework, try to post it there first so everyone can see the answer. But of course, you can always write me an email, but it might take a bit longer to reply. Yeah, I'm being asked if I'm going to upload the whiteboard. I'm going to. It is a bit messy. I'm sorry, but it is just as it is. The book is really well written and it's really neat. But the whiteboard is just, you know, to help me try to explain the topic. So don't expect it to be. I'm not retouching it. I'm just uploading it as it is. Okay. Any more questions? Okay, so that was it. Expect the homework by Friday morning, and yeah, good luck with that. And we'll see you next Monday for fluid statics. Okay, thank you very much.